if you're using Solr, uh, you cannot use it without putting data in it. So I'm going to talk about how can you scale your data ingestion process and how we encountered problems with the traditional way of doing it at Wayfair, and how we changed it recently, and how we are reaping benefits from it. So just to get a sense of how everyone is using Solr, raise your hand if you are using some kind of a persistent storage to pull your data from into Solr. A lot of people. So when you have a persistent storage that you have to pull data from, there are inherent delays that would happen, especially if you're using Solr for a purpose which requires data that needs to be up to date. For example, in e-commerce, there are certain things that are, if the data is stale, you're going to have problems. So this talk will cover. I'll talk about all those potential problems that you can have with stale data, and then the kind of problems that we had at Wayfair and how we started thinking about solving it, and the kind of solution that we developed afterwards. And so we have been using it for a few months now. So I will also share some tips and tricks that we have learned so far in that process. So a little bit about me. I started working in search in 2013. I joined Wayfair 2 years after that. Initially, I was working on things such as natural language processing, improving search relevance, and the typical interesting things in search. Last year, along with my colleague John, we also gave a talk on how to mine information from reviews and use it to improve your search experience. After that, I realized that the way the relevance tuning is important for search. Another important factor is data freshness. So that's why we created sort of a dedicated focus team called Search Data Pipeline Team. I'm currently leading it right now, and we are trying to build a platform that is helping us ingest data much faster. And this is the talk about that platform. So this is how we'll go. I'll talk about search at Wayfair, and then I'll talk about the exact data ingestion problem and how we try to solve it. And after that, I'll give you a little bit details of how the new event streaming platform is structured, and some lessons learned, and hopefully we'll have some time for question and answers in the end. So if you don't know Wayfair, the company actually started in 2002. It was branded to Wayfair 2011, and we went public in 2014. It's not just Wayfair. There are four more brands which are dedicated to different categories of furniture, different styles, different customer. So total 5 brands, and Wayfair brand itself has a presence in US, Canada, Germany, and UK. So there are 8 different stores, 4 countries, and millions of products for sale. And the company is growing quite a lot, like almost 15,000 people working for it right now. Financially also is doing well, especially after it went public. The revenue is growing a lot. These graphs don't give you a large, I would say, like a bird's eye view of what's happening in the furniture market. So you know that like everything else, furniture market is moving online. It is moving slowly, but definitely more and more people are buying furniture online. So last year, of the money that moved in the home goods domain online, Wayfair captured 35% of that money. And we just opened a brand new store in Massachusetts. If you happen to be in Boston area, do visit it. It's really gorgeous from inside. Here's one more picture of it. Okay, so let's get back to business. So search at Wayfair is like any e-commerce site. Like we have search suggestions. You type something, you are taken to different pages, and this was something that I mentioned in my last talk. Keyword search, also the regular browsing, the sorting and filtering, the customer reviews, also some dedicated pages such as the sales section of the website, because it works a little differently than the regular browsing. And we are also using search in a lot of internal applications, as well as some other less known, less explored areas of the website, such as you can go to the inspiration gallery, search about what kind of things you like, and you will get inspirational pictures, and then you can buy items tagged in those pictures, things like that. So the way the search has been expanding at Wayfair, We are still, there was a time when we were like almost 100% of our data was coming from a single persistent storage, like a SQL server. And this is where the data ingestion challenge comes into picture. And I think I believe like most of the companies still have the model of data movement into Solr in the similar fashion, where you either have like HBase or Hadoop or something else. Mostly it's SQL that you have to pull data from. Now, before I proceed, I want to make it clear that this talk is not about when you search for scaling the ingestion at search, like people talk about how to configure the SolrCloud, how to shard your indexes, how to do JVM tuning. I'm not going to talk about all those things. There's enough material out there already. I'm going to talk about the ETL pipeline because you can do really cool things when your data reaches Solr, but there is less unexplored or more unexplored space in the ETL domain that we talk about at Solr conferences. And I'm just making an attempt to address that part. So let's get back to this diagram. Millions of products, millions of updates happening every day. I think we get about 3-digit millions of updates every day from constantly changing information sources such as pricing, dynamic pricing algorithms, out-of-stock statuses, and different product additions and things like that. And everything is processed through database. And as you can imagine, the database always is on fire. And when that happens, you can guess that everything is just slow. And I think it's anyone's guess, like what happens when your database is slow. Can anyone guess? What happens on the search side? Yeah, I mean, you basically are serving stale data to your customers because everything is slow. So when the product goes out of stock, that status is still sitting in the database, and it takes minutes and hours for you to actually show up in SolrCloud. That means the customer would try to buy it, and then in the end, we'll have a disappointment. So this is an example, like if you are powering your browsing information from your SolrCloud, the customer is searching for pillows. They really like that cute pillow, and they click on it, they try to buy it, it's out of stock. Right? We don't realize it, but it could really be heartbreak for someone. And as a Solr engineer, we try to have a better customer experience, definitely not heartbreak. And it's not just out-of-stock status. The data staleness is your enemy everywhere, even outside of search domain. Like sometimes there is a data inconsistency between the actual status of the product in the warehouse and the status in the database, and you actually are able to place the order successfully, but the data, when it reaches warehouse, they say they cannot fulfill it. That's even worse. So fresh data is, I would say, is somewhat neglected pillar of having an awesome search experience. You cannot have awesome search experience even though you have really fast search and really relevant result, but that data doesn't make sense because it's not fresh. So now let's dig into what kind of data we are talking about, especially for e-commerce. So the product data that you serve through your SolrCloud is composed of different pieces. And to give you an example, product catalog, which contains just the basic metadata about product, the name, description, what filters you can apply, the inventory information, delivery guarantee, can you deliver it in 2 days, 3 days, sale, pricing, and so much information. And typically, since there's like a lot of high volume transactions happening, it makes sense to keep them in the different databases for different purposes, including fault tolerance. So your job as a Solr engineer is to pull all this data into SolrCloud and constantly, as fast as you can, and keep it up to date. So what we did initially was we said, okay, why don't we just create a new database and use database replication, put this into one single place so that we can run a single query and pull all the data, right? Brilliant. That was brilliant like 10 years ago. Now, that probably doesn't make sense, and I'll show you how. So I think we started using Solr like 10 years ago, and earlier it was like a sort of a slow progress, but since we went public, since we started scaling, like more and more people coming to Wayfair, we started making rapid changes, and I will just give you a short overview of what we did. So as I said, like we had a giant stored procedure which ran for hours, pulling all the data, and that means we could only refresh our index once a day. That was probably fine when Wayfair was not really well known. But then we quickly realized that we need to update data faster. So we went to incremental indexing. And if you know what incremental indexing is, basically you have to split your data processing into different steps. You store snapshot of different data in different steps. And you have some kind of tracking tables that track what changed. And you only process the change data so that you can probably do it multiple times a day. And you have to process much less data. But now on the side, what happens is that you are basically adding more storage to your database. You're making your database bigger. In processing, you're using a lot of temp tables, and there is a lot of shared tables which are processed in different stages, so you increase chance of blocking. There are all kinds of problems that you run into. But it's very hard to get out of the database, I'll tell you. So what we did was, okay, now since there is incremental indexing, all the changes are basically processed in a first-come, first basis. But now some things have like more important, some things are higher priority than the other. Like for example, if something goes out of stock, you probably want to process that much faster than when someone changes like a product name or something. So we said like, okay, let's implement a update funnel system with a priority queue. So all the different areas where we get the data from, we will put them into a single processing queue and assign it a priority so that we can process the high priority data ahead of the low priority data. So this sounds like a good idea at first, but you quickly realize that if, let's say, I'll give you an example. Like let's say there is a pricing job that finished, and dynamic pricing job basically changed 50% of the prices on the site. So you have millions of updates sitting in that queue, and it is a second priority, and then there is a quick attribute change that you need to make, which is a low priority. So until those millions of changes are processed, the other changes will wait behind that queue. So we said, okay, so we'll try to address this by adding a hybrid priority where we'll have a time wait as well. So data will sit ahead of the high priority data only for a certain time. And this worked well. Basically, it made things a little better. And this is how it works. Like this is a snapshot of, I don't know how it shows up. Like, are you seeing colors correctly? Okay. So the yellow is high priority, blue is low priority, and you can see that the blue is waiting, the yellow is getting processed, and then after some time, it has waited long enough that now the purple and the blue is getting processed at the same time. But that means if you look at on the x-axis, it's time, your data can still sit long enough in the queue. And if you're using single server database, you still like have troubles. So it reduced the wait time for high priority updates, but then since there's a priority, there is more computation happening, more dynamic comparison happening in the database, and we are basically putting database under fire. Then we heard the name Kafka somewhere, and we said, okay, let's just use it. So we said, okay, if we use Kafka, all of our problem will be solved. So we put Kafka in between database and Solr, and so it gave us some benefits because now the Solr doesn't have to query database directly. We can query data to database and then put it into Kafka. So that means we can replay the traffic to Solr when we have loss of data. We don't need to query database. So there are some advantages, but then since you are still pulling the data to database, you are not improving on your latency. You are just getting additional features, but not really any significant improvement in how long it takes for your change to show up in Solr. And this is a snapshot from SolarWinds on a typical day where there's a lot of blocking on our database, and like memory usage ran 100% all the time and things like that. So we realized that even though database made things easy for us to process everything in one place, that turned out to be the villain. The database, we need to find a way to kill the database. Now, when you think about killing the database, it's not like, it's shocking. Like everything is stored in database. How can you kill the database? So think about this diagram again. Database is your source of data. You kill the orange colored Solr database, but you have to still get it from the inventory database. I'm just giving an inventory example. But if you think a little carefully, the actual data source is not the database. So the data source is the service which is writing into the database, and you need to find a way that creates a sort of a fast route between that service and Solr. And that means you need to use streaming. But now there are suddenly many questions arise. Like database made things very easy. You can just assume everything is right in the database. When you use streaming, how can you ensure the data is right? And you will have so many question marks. So if you have been using Kafka, or if you're a little bit familiar with streaming, or if I'll give you some overview of what streaming exactly is. And I think if you understand it well, you'll feel much more confident switching to streaming than just using your database tables. So the question is, can you replace a table by a stream? So let's look at it. If you have read this blog from jcreeps, and if you know who jcreeps is, anyone knows who jcreeps is? Yeah, he's not Tom Cruise, but if you've used Kafka, you'll know him. He is the CEO of Confluent, who owns Kafka. So he wrote this blog when he was working for LinkedIn in a few years ago. And this blog basically talks about how the transaction log or the stream data is equivalent to a table, and how understanding this changes your perception of table versus stream. I will definitely recommend you reading this blog. So this is an example of what basically it means. So let's say in the red you have this table, and in the blue you have the data stream for banking transactions. So Alice has $50. Alice adds 50. I don't know. It's euros. 50. We'll call it dollars. We are in the US. So Alice adds $50 to its account, and then the next transaction comes in, and the next transaction comes in, and as the transactions are flowing in, the state of the table is changing. So if you try to ponder over this, you'll realize suddenly that this table is nothing but a stream frozen in time. You can literally reconstruct a table if I give you a snapshot of the stream by just replaying all the transactions. So this is exactly the concept behind Kafka. So that means if you handle the stream well, you can easily replace, you can easily assume that it will have the same data as the table if you don't lose any data in the stream. So okay, so how do you do this? If you look up how to get the event stream from database, there is if you've been using SQL, there is a lot of change log that you can capture, change transaction log you can capture, and you can easily create Kafka stream out of it. But if you do this, you will still not get the benefit. Why? Because a number of reasons. First is that the change log is generated per table. That means you can only create one stream from one table. And we are processed, for example, at Wayfair, we process from hundreds of tables, and it doesn't make sense to create 100 different streams to generate from those tables and then start processing them outside. It's essentially just replicating all your data outside of database. It can still make sense if you're working with really small number of tables and you just want to avoid database at all. But since the data is still getting written into database, you will not get that latency improvement. So can we do this? When the service that generates the data is writing into database, it also writes into the stream. That's possible, but it's a little tricky because what happens if your database transaction fails? Right? What happens if your stream connection fails? Right? So obviously these are practical issues, but it's not it's not possible, because you can do it in such a way that when you write to database, you also write to the stream and make sure that the database transaction is committed, and then you write into the stream or things like that. Or you can also have another Kafka topic between your job and database, so that you only write to Kafka topics, and even if the transaction fails, you can just replay the traffic from Kafka. So there are a number of ways to address this. But the point here is that if your application, which is generating the data, is creating the event stream, then things get much more interesting. So let's say you have event stream from one source, you have event stream from other source, inventory, product catalog, pricing. Now what do you do with it? You need to find a way to combine these event stream and join this data and put it into Solr, right? So obviously there are tools available like Spark, Flink, Samza, Kafka Connect. You can use all these things to just process stream data, but we could not make a decision. We could not decide which one, because if you read description of each of these online, they exactly sound the same. It's like a big data distributed processing platform which gives you the statefulness. So same thing, right? So either you just experiment or you just stick to one, whichever your company is using, or you try to understand how the streaming join works. This is what we did. So let's assume that you have a product catalog stream which gives you information about the new products that are added on your website or changed or deleted, and another stream of inventory which is giving you information about in-stock, out-of-stock status. So let's say you add a product, new product on your website, and obviously it is in stock, so you can expect these two events to show up in the streams almost at the same time, right? So let's say you're monitoring these two streams, and then you got a product addition event, and then within a few minutes you can probably expect the in-stock event as well. So you don't really have to wait really long, right? So it's much easier in that case. But let's say the product was not really popular. It had few units sitting in your warehouse. Over the time, it got sold out, and after 1 year, it becomes out of stock. Now, in that case, what happens is that the out-of-stock event shows up in the event stream for inventory, but where is your product data that you want to join it with, right? If you're using Kafka or in event stream, you can only consume the next record. You cannot really look up records by key. So the first basic principle of being able to join two data streams in the conceptual, like in the SQL equivalent of that is an inner join, is that you need to be able to look up any key that you want to have data, you want to obtain its data from the event stream into some kind of a key value lookup. And that lookup is called as state. So if you, let's say, in order to do the streaming join, you need to have something that builds the state of these streams in some kind of storage. So let's say the first component we need is a stream state builder. So it listens to each stream and puts all the key value lookup data in some kind of a storage. And then when you need to join this record, you need another component that has a logic like how to join these records in different ways and then produce the join output. Now, if you're using Spark or Flink, you can also do these things using those technologies. The only problem is that when you do a join, you have to specify a window. They have a window join concept. That means if you have to know within how much time window or whatever unit you're using, you will expect the other key to show up. So that doesn't really work with all kinds of data. You cannot really specify a window of 1 year or 2 years. And that may not even guarantee you that it will work. I think Spark and I think Flink is much better at it right now, and Spark is also moving towards having some kind of a full state storage in the processing. But when we started working on this, there was no system which was doing this. But it seems like very simple. Like you just need to create a state holder and then some component to join those streams and produce output. It was it's very simple. So we created a platform called Siphon. It's actually the same name that we used for the earlier system, but now we call it as New Siphon. But we used a external state storage Aerospike. You don't have to use Aerospike. It could be any key value lookup like Redis, or even if you like Spark and Apache Flink, they use RockDB for having a persistent storage on the disk itself. But depending on your requirement or speed requirements, Aerospike is really fast, distributed cache, good replication, great support. We use Aerospike for storing our external state storage, and we use Siphon to basically create these streams and join this data and put it into Solr. So this completes the journey of the data, the evolution of data pipeline that we have at Wayfair. And now let's look at how the Siphon works internally. So Siphon is basically a Java platform. It can ingest data from multiple sources like SQL, Kafka, any REST API. It has two different components, which are the extract jobs, which basically is nothing but a state builder. It listens to streams and creates your states in Aerospike. And the publish job is basically has the logic, because we have multiple sets in Aerospike. So you need to know which sets to join. So that logic is all in the publish jobs. And then there is a task manager which can run and combine any source into any published destination. So that's task manager, and obviously you need connectors and services that are listening to each service endpoints that you have. And we have a nice REST API along with the admin UI to manage all the jobs. And this is how the UI looks like. You can select what kind of job you want to run. You can produce all the parameters, and it will make a REST call and kick off this job. Then you can monitor all these jobs on the UI. You can interact with them. If there is any stuck job, you can restart it and things like that. And this is how it works internally. So on the top, what you have is a each box representing a data source, and each data, and the green ones are the extract jobs. The red one is a publish job. So let's say, so this in this diagram, what we are doing is we are trying to combine data from 3 different sources: a SQL, a Redis endpoint, and a REST endpoint, and try to combine this data and put it into SolrCloud. So what's happening is whenever there is a change in product catalog, I'm getting an event notification via Kafka. And whenever there is a change in Redis endpoint, I'm also getting event notification in Kafka. And the good thing about Siphon is that it doesn't have to be notification based all the time, because not 100% of your data needs to come from streams. You can still consume it from database. But now, since you have moved your high priority data into streams, the load on your database is much reduced. Like in our case, it was reduced to almost 30% in terms of execution time. So the short procedure, let's say if it took 100 minutes to run, now it runs in 30 minutes, because all our high priority data now sits outside of database. So when you get a notification, change notification, the extract jobs basically update the state in Aerospike, and they also send a notification for the publish job to tell that that this state has changed. So the publish job is listening to that Kafka topic, and whenever the state of at least one of the stream changes, it just looks up the same key into all respective set states, and then combines the document using a simple join and publish it to SolrCloud. And obviously, we are monitoring, like we monitor throughput. It's very fast. I don't need to explain all these numbers to you, but we ran like an experiment with this recently, where in one of the SolrCloud cluster, we sent the data through our old database-based pipeline for a few hours overnight, and in another cluster, we sent data over using the new pipeline, using event streaming. And this is the inventory data, so on the y-axis, you will see that it is indicating how much percentage of data in Solr is stale. So you can see that all the peaks that are going up essentially represent the overnight build jobs are finishing, and they're dumping lots of data into database, and that takes like very long time slowly to process through database, while in streaming, there is hardly any peak like that. And these are some numbers like across the stores that we were testing. The max staleness overnight in the database-based pipeline was around 30%, versus it was 9%, but except that 9% on the right, everything else is like less than 1%. So the 9% was there because we identified another problem with that, where the Siphon was producing data so fast that one of our collection was not able to ingest it. So we are now working on sharding it so that it can consume the data much faster. But this is a good problem to have than the otherwise. So average staleness, I would say, was like 10 times better with this. So this was sort of a journey that we had in last few years. Like from hours of delays in waiting for data, now we are in a position that we can have delays less than 1 minute. From the heavy database dependency, we are switching to we are still in the process of doing it. Not 100% there, but the Kafka streaming using external state store, real-time. So we are trying to get to a real-time update phase for certain high-priority data such as inventory and pricing. And the delays, which were in minutes and hours, now are like much lower. So now lessons learned. Any questions so far? So we have like several collections, and overall, it's like somewhere between 80 and 100 million documents.
Do you perform any enrichment in this process, or is the data that you receive already in a format that you want to ingest?
Yeah, so there is some processing that happens. So we try to minimize that. So the question is there any enrichment in this data pipeline that we're talking about? So we try to avoid it, but obviously you cannot avoid it 100%. So the way to handle that is that in the ingest job that you write on Siphon, you can essentially add that logic to pre-process your data. Or if, let's say, for example, if you're using multi-valued fields, and the data that you're getting has some kind of separator to indicate different multi-values, you have to split that. So all those data transformations we are definitely doing. And it's a choice that you have. Like if you think your Solr can handle those, you can specify that in your Solr transformers. or you can also have that on the Siphon side, which is the platform that I'm talking about. So we kind of have it split. Like some transformation happens on Solr side, some happens in Siphon. And if you remember the notification diagram that I showed, like a significant portion of data still comes from the database. And the database, that means you can do the kind of any query you want and process the data in the database itself. So the key is, like, if you identify your high priority data sources and convert them to event streams, that's where you'll get the most bang for the money. So what we saw was almost everyone does this. Somebody produces data in the database or some kind of persistent storage, HBase, and then puts the data into Solr. And then it's not just Solr, like there are many other services in the company that are trying to consume that data. And definitely this is like not scalable, right? This won't scale if your company grows. So there are some of the strategies you can use. It's like, I think the one that works the most easy to do is when you write into database, you also write into a stream. And make sure, or I didn't indicate that you can also have a Kafka topic in between database and data producer, so that you get that guarantee that once you write into the stream, it will make into the database no matter what. And the second strategy is, which I did not mention earlier, is that like in this strategy, I'm saying that you write all your data into Kafka. That means in Kafka, you have to have a key and the payload. For example, if you're sending data for product information, so it has 10 fields. So you'll write all those 10 fields into Kafka. So it has some advantages that you can get your data from one source, but the disadvantage is that if your data format changes, or if you have too many streams, then it puts several storage load on your Kafka infrastructure. So you have to be careful about it. But I think the better way is that you expose some kind of an endpoint using a distributed cache. So this is not the Aerospike that that we are using, but you can use any key value store to sort of make your data available via key value lookup and wrap it around a service layer. And then when that data changes, you create a stream of notifications that anyone in your company can listen to. So let's say you are producing data you're producing some kind of data that many people in your company need, right? So typically we write the data into database, and then data scientists wants to use that, they pull that over somewhere else. Solr people will pull that somewhere else. Analytics people will pull that somewhere else. Instead, if you just publish that in some kind of a key value lookup and create a change event stream, then that means that will also encourage other people in the company to sort of switch to event streaming. And that means the data lives in only one place, and it is really accessible via a fast interface. And then obviously you need application like Siphon, or you can use something like Flink or Aerospike also as well, if you don't really need that 1 year long window to combine this data. So that's the third strategy. Like, you need to have a way to combine this data together so that you can produce data output. If you produce data output, like right now we are producing output in Solr only, but we can easily write into Kafka, and then like there could be multiple consumers of the data, not just the search team. So some of the tips or some of the things that we encountered while doing this is the cold start problem. When you're starting up for the first time with event streams and state, you need to build the whole state in memory first, right? Because there could be data that is not changing in next few days, and if there is a lookup that you need to do, so you need to do this by uploading all your data into that state first, and you need to find a way to do that. Sometimes it may take a long time. Like, for example, in our case, it takes hours for the inventory service team to pull all their data, all historical data, and put it into our state. But once it is done, you can pretty much rely on it, and you will only process changes after that. You can also use Kafka replay. Like, for example, if there is let's say you solve the cold start problem, like you have the data in the state, and for some reason that state is corrupted, or there is some problem with your key value server, and you lose that data. Then since you have Kafka, you can use the replay feature of Kafka to build that state again very quickly, versus it will take very long time if you're pulling that data from database. And since now you're basically creating a highway of your high priority data to get into Solr, you can also expect that the bad data can also slip into your Solr very fast. And it happened to us in the beginning that like some field had a bad like missing value, and it basically got into Solr before even we realized that like most of our index had that bad value, and it started affecting customers. Like they were not seeing some products results correctly, so we had to do like a lot of manual efforts there to correct that data. But if you remember that, then there are some strategies that you can use to avoid this. Is basically let's say if some of the fields in your Solr Solr index are really cannot be empty, right? For example, that could be one condition. And if you get an empty data, the Solr should reject that document. You can mark fields as required in Solr, or you can also enforce that check when you're ingesting in your data platform like Siphon. And also data formats consistency. This is a big thing because initially, because every team does not understand the format of the other team, right? And if you are talking about multiple teams consuming data from streams, this data format will eventually become a problem. And I don't know if there is a great solution for managing this across the organization. Like ideally, what I want is like if there is a way where anybody can query and say, okay, this is the format that this service publishes data in, and I need to align my data consumption in that manner, so that there is no confusion. Like if you send them some format and tomorrow you change it, you need to manually tell them that it is changed. But instead, if there is like a central place to do that, it's much easier to manage. Or you can also do schema checks on your side, but that's a big headache. Like we're trying to avoid it. Have you heard of schema registry? I think I've heard about it in Kafka, but I've not really used it. But I think this is like one of the attempts to solve that problem, where you have like a central registry of schema, and once you say that my topic is going to conform to this particular schema ID in the schema registry, so anybody who is trying to consume that will be using that reference while consuming your data. So if you change your data format, you will update the schema registry, and they will also know about that change. And understand that like not all data is stream worthy. It could be hassle initially to set this up and manage. So it only makes sense to do this for your high priority data. Like if you're really worried about, I think for e-commerce, the things such as that I talked about, like inventory, pricing, these are like really high priority updates. It like impacts customer more if that data is stale. So you want to get that data on your stream rather than things that don't matter, such as product names and things like that. And don't forget DB. Like I know I've been cursing DB a lot, but DB is still your savior, especially when there is any problem with your system or there's something that is incomprehensible happening. Then you can always go back to DB and say, okay, now I need to do like a full load from DB, restore everything, and make sure that my data is consistent from database. I hope that you need to do this less often, but don't abandon it so fast. All right, yeah, so it will be useful for streaming. And that's about it. Any? Yeah, we can have questions now.
I do have a question. This is really cool, but how did you handle like you say you only can save about 1 year of the data update. Then how about the data, for example, the data update you have is not in the, for example, you have showing the pricing with the inventory, but the previous inventory is not in the streaming, the streaming storage you have.
Yeah. So I gave 1 year as an example. So the question is, what happens if you're using window of 1 year and then the data that you need to look up was changed 1 year before? Yeah. So I don't think if I came it that way, it is my mistake. But I'm saying while solving the cold start problem, you have to send the data from the beginning of time. Basically, all the records that you care about needs to go there, not just like 1 year worth of data.
Your story or your cache?
I mean, if you talk about e-commerce, you have finite set of SKUs that you need to worry about. So it's not really infinite data there. But let's say if you're talking about clickstream data, then obviously you don't want to use something like this because clickstream, all the keys, all the instances are unique, and you don't want to hold everything in memory.
Do you have like multiple database, like when you reference product catalog, is that the master system, or you have a master system and the catalog is another instance for the site?
So the question is the product catalog that I referred was a master database or like a copy of it? So there is obviously a master database, but I showed that initially that we replicate that data over using DB replication into another database. But when in terms of streaming, the original creator of the data is creating that stream. So you can treat it as a master copy, but obviously like you don't want to use that for your transaction management. That's only for read-only. Please.
How often do you keep your retention in your Kafka streams?
Oh, retention?
Yeah.
So since Kafka retains all your data, you only need to worry about, so the question is how much is the retention on our Kafka topics? So it really depends on how often your data changes. If your data changes really fast, you don't need to have really long retention. But if you know how Kafka works, like even though you have very short retention, at least one record for each key that has a unique key that is made on Kafka will still be stored. So the retention only works for the keys that are duplicate. All right, so we are almost at the end of this. I'm happy to answer more questions after this, outside or even in the conference party. So thank you very much again. That's it. Thank you.